I will move on. Sorry about that distraction. So I will pause a little later to see if I can fix my audio because I cannot hear anybody in the room. However, if you have a question, please make a note of it, and maybe when I get through, we can get that fixed. So NIRCAM has two identical halves, which is important because it's also the telescope wavefront sensor, in addition to being the near-infrared camera. It's refractive in design, and there are dichroics that allow seeing the same field in both short and also long wavelengths here. Then that allows two different imaging scales for 2 and 4 microns. And we have dispersive components that allow slitless spectroscopy. So, and then the scientific mode that's supported in cycle 1 is going to be in the long wavelength channel. So from 2.5 to 4 microns of slitless spectroscopy. I will take just 1 second to try to switch my WebEx audio to see if I can hear you. Oh, I can hear you all again now. Okay, thank you. So I will continue. The way that any mode in NIRCAM is selected, it's just through simple filter wheels. Light comes in from the telescope here, and then hits usually does not hit the chronograph masks unless they're selected, then hits a dichroic with the short wavelengths going into this channel where you can select both a pupil and also a filter wheel component. They're right next to each other. So you can do imaging here in the short wavelengths while the long wavelength light comes through the dichroic. And you can do spectroscopy here. You can select these grisms. We have 2 different grisms with the same resolution but different dispersion directions. And the wavelength range is then selected by which filter you want to match with the grism. And I'll show you some examples of that. This is an example spectrum taken with NIRCAM. This is during the instrument testing at NASA Goddard. I think this was in CV2. Here is a NIRCAM field. It's 2.2 by 2.2 arc minutes. This is a spectrum of a point source that was in the ground support equipment called the OSIM. And it's dispersed so that longer wavelengths go this way. And very conveniently, sort of by not by design, there was a CO2 absorption feature. There's some ice not in NIRCAM or the rest of the ISIM, but also it was just on the test equipment here. And this is the extracted spectrum, and you can see how this is that this dip here is that absorption little blob in the middle, and the flux fell off not because of NIRCAM, but just because of the test equipment in that test. So this is just an example where this spectrum is taken through this particular filter that goes from 4 to 5 microns, this F444W filter, and the dispersion with all spectroscopy is pretty close to 10.0 angstroms per pixel. And the pixels in the long wavelength side are this 65 by 65 milliarc seconds. And they're it's 2 pixels per diffraction element at 4 microns. This is an example of the spectral coverage you get through some of the filters. There are more than these allowed over on the left side of the plot. The blue is this 322W2. It's a very wide filter. It's probably going to be popular for some transit observations because it covers water at 3 microns and also methane at 3.4. Then so we can get one chunk of spectrum with the blue or one chunk of spectrum with the green, which, for example, you may want to do for some wide field surveys. And this is another filter that could get this chunk of spectrum here. And on top of this is the GRISM response function here. So this is shows you the efficiency of the GRISM, just the blaze function, and the transmission. And this has to be multiplied by the filter curves to get the throughput. Then on the right side shows the spectral resolution as a function of wavelength. This is again, everything is slitless, so the size of the PSF largely determines the spectral resolution at each wavelength. Here at the shorter wavelengths, it's undersampled until you get to about 4 microns. That's the 2-pixel Nyquist sampling wavelength. And from here, it starts to level off because it becomes diffraction limited. Then this table shows the filters that are allowed in this single object time series mode. So we've got 4 here of different widths. I think I showed 3 of them on the previous plot. This is this column, 5th column here shows the fractional length they take up on the detector. So this wide one takes up 77% of the width of the detector, and they all operate in first order. Then these will probably be the most popular ones for transit spectroscopy at the top. This 322W2 and the 444W. And with the 2 of them, you get 2.4 to 5 microns. So it does require 2 observations, though, to span that whole wavelength range. So this is a table of the continuum and line sensitivities for single objects and the saturation limits at different wavelengths. And I've just computed them for these 2 wide filters. They do change a little bit if you use different filters. If you use a more narrow filter, the sensitivity gets better because there's less background coming in. And the saturation limits won't change much, though. So you see, you can look at quite bright stars if you're interested in, for example, host stars of transiting planets. And then this example here is for, let's see, it's 80% full well with 2 reads, so 2 frames per integration using our smallest subarray, this 2048 by 64 pixels. So we can look at almost any known transiting planet star with NIRCAM, particularly with these longer wavelengths. As just to show you some of the modes here, I have just popped up an image of the APT time series template. As I said, NIRCAM has 2 identical modules. We just use one of them for time series, the A module. It has better coatings on the GRISMs, so we'll get a little better throughput. We have 4 subarray choices here. So this, they're 64, 128, 256, and full height by 2048 in length. Then we can also choose a number of outputs. So this allows to read the detector faster. If you have really bright stars, that those saturation limits were for the 4 outputs. Then we can choose what we want to image simultaneously at the short wavelengths while we're taking spectra at the longer wavelengths. Then we pick the filter here to go with the GRISM to set the wavelength coverage, and then the readout pattern. And you pick the number of groups to match the integration time you want, and the number of integrations to match the series. This is just setting up the exposure, and APT tells you how long you're integrating. So there is one of the things I like to point out at the short wavelength, this option here is with a weak lens, so it'll actually spread out the light at short wavelengths while you're taking a spectrum at long wavelengths. So 1, you won't saturate, and 2, you'll get better spatial sampling and hopefully better precision on your image. There's no dithering in these templates. This shows a little bit about the target acquisition. The blue arrows in these 2 plots show the undeviated wavelengths. So that's where the light goes straight through. If you put the point source here, you will get the spectra with this filter, this Grism filter, so that short wavelengths over here, long wavelengths are over there. And if you put in this other filter, this 444W, then the dispersion's in the same direction with longer wavelengths to the left. And you can see that we've tried to set these so that the spectra overlap using the same pixels as much as possible. So we always want to use the same pixels for spectroscopy so we could calibrate them out well. We may, probably will likely change a little bit where the spectra are vertically, because we want to be able to, for the smaller subarrays, be able to get reference pixels near the edge of the detector. Okay. Just, I don't want to say a lot about the pipeline, but NIRCAM will use the time series data pipeline that is being developed for all of James Webb, particularly very similar for all of the near-infrared instruments. Mary will have a little bit of different ramps to slopes corrections, but the raw data come in and sort of like the basic data checks happen with bad pixels get masked, check for saturations, use the reference pixels to subtract off biases, apply linearities, subtract darks, then fit the ramps, and do any sort of sky fitting, do wavelength calibrations, spectral extractions, and then this is done at different levels. So you do the separate spectral extractions for each individual integration, and also in a sums one for will be the final product. Also, the one feature of this time series pipeline is it produces a white light curve. So you can actually see the time series from all of the spectral pixels added up. Just like the other pipelines, this one will be able to be downloaded, and you can rerun it yourself with small tweaks or taking steps out. This is the little preview of a possible future mode. There are some spectral elements in the short wavelength side of NIRCAM, so it's not the side of doing the spectra I showed earlier, but this actually disperses the light if you have a star. This is actually designed for wavefront sensing, for phasing the mirror, but once it's phased, it works like a spectrograph. So a single star gets split into these 10 different spectra, and then they get dispersed from 1 micron to 2 microns using 2 of the near-infrared detectors. They're just adjacent like this with a small gap of a few hundredths of a micron in between. So this has some nice properties of spreading the light out so we can look at very bright stars and get good spatial sampling. However, this is not an approved science mode for cycle 1, and also there may be some limitations when we actually start using it with the Grisms, like we may need to use the same subarray. So if you have a really bright star, you may not be able to get all 10 spectra. So this is under study, and just a preview of what may be coming down later in future cycles. That is pretty much what I wanted to say. Happy to take any questions, and I would like to leave up this slide with some further information, general information about NIRCAM. There's a recent paper on slitless spectroscopy. There's an upcoming meeting in SCI on data analysis, and it's worthwhile to download and explore a bit with APT. And hopefully we'll be getting an exposure time calculator in January. And if you have any questions until then, please contact me or another NIRCAM team member, and we could help with any sort of simulations. Thank you.